so there you go. Radical expression and rational exponents, right? So this unit, right? We kicked things off this unit with looking at finding the inverse of simple quadratic functions, right? And that involved using square roots, and we had then functions with square roots in it, right? And then yesterday we did finding inverse functions of cubic functions, which involved using cube roots, right? And we graphed both of those. We graphed square roots, we graphed cube roots, all right? And so, if you remember in our past units, right, not long after we learned graphing, whatever particular parent function it was, right? So not long after we graphed quadratics, or not long after we graphed, cubics or polynomials, we then learned how to solve and simplify those expressions that involve those things, and then we eventually also solved equations with those things, right? So we start with expressions. Because expressions, right, they don't have an equal sign. We're just simplifying, right? Sometimes we're rewriting, sometimes we're going to combine terms, stuff like that. And that's what we're going to do today. And then eventually, tomorrow maybe, I forget exactly. At some point, we're going to be solving equations, all right? We have a little light friend over there that's just floating around. All right, someone's reflecting. Anyway, it must be Julia, I bet. So anyway, okay, so, yeah, let's get into things here, okay? So, let's see here. How do I want to start? All right, okay. So here's what we're going to do. We're going to start into this, right? So we're going to be taking radical expressions, and radical is just from the word root, okay? So radical in Latin, right? The base for the word radical is radix, and in radix, in Latin, radix is root. All right, so that's why we kind of use the word radical or root kind of interchangeably, because they really mean the same thing. I guess that's why the word radish is word radish, because it's also kind of like a root vegetable, right? Comes from the ground and stuff like that. So anyway, language is neat. But let's see here, because we want to ask the question here, okay, how can you express the square root of a using an exponent? Okay? Do any of you guys know what square root of a is as an exponent? It would be a to what exponent? 1? Okay. 2? All right. 0? Okay. Well, we'll see here. Okay? So yeah, square root of a can be expressed as an exponent. So let me show you how we're going to do that here. All right? Let's just hypothesize, right? Okay, if this can be expressed as an exponent, then we'll have something like this. The square root of a equals a to this mystery number m. Okay? So if the square root has an exponent, right, if square root has an equivalent exponent, it'll be equivalent to a to the m, right? The square root of a is going to equal a to the m. All right? So now, how do we simplify from here? Well, let's undo this square root. So what undoes a square root? How do we undo a square root? What cancels it out? Square, right? We're going to square both sides. We'll square this side, and we'll square this side too. Okay? So when I square the square root of a, what do I get here? Just a, right? And if it's just a by itself, that means what exponent does it have here? A 1, right? Okay. Now, here when I have a to the m to the 2, do you guys remember your exponent properties? When we have a power raised to a power, how do these simplify? What do we do with these two things? Not add them. We're going to multiply them, yeah. If we have a squared times a to the 3rd, that becomes a to the 6th. Nope, I can't add. Goodness, a to the 5th. Sorry. When you multiply two numbers that have the same base, you add their exponents, right? So a squared times a to the 3rd becomes a to the 5th. If you have a to the 2 and then to the 3, that becomes a to the 6th. That's where you multiply their exponents, okay? So a to the 2 times a to the 3 becomes 5, but a to the 2 times to the 3rd becomes a to the 6th. Okay, so here this is going to become a to the 2m. All right, now, since these two things are equal, right, and they both have the base of a, but this one has an exponent of 1, and this one has an exponent of 2m, right? So we know these two things are equal, They have the same base number. They both have a as their base, but their exponents are a little bit different. This one's 1 and this one's 2m. But if these two things are going to be equal, what must be true about their exponents? If they have the same base, what also must be true about their exponents? They must be what? The same as well. So we can kind of forget about the a's and just say, okay, that means 1 must equal 2m. Okay, must be true. If we're going to say these two things are equal, okay, then that means that the powers must be the same too, since they have the same base. All right, so now, well, what can we do here to solve for m? What's with the m that we can get rid of? It's 2, right? So how will we get rid of that 2? Yeah, divide both sides by 2 now. And we get m equals 1/2. So back up here to our original question, the square root of a, which was equal to a to the m, okay, right? Well, that resulted in m being 1/2. So the square root of a is the same thing as a to the 1/2 power. The square root of a is equal to a to the 1/2 power. Okay? Now, I can use a similar argument here to do something similar for a cube root. All right, but I bet you guys can figure it out just because we're so good at recognizing patterns, right? So, if the square root of a was the same as a to the 1/2, what do you think the cube root of a is going to be the same as? A to the what? 1/3. Okay, and then the 4th root of a, that's a to the 1/4, and then the 5th root of a, you get the idea, right? Okay, so on and so forth. Okay. So a root becomes the denominator, okay, of a fraction. A root becomes the denominator of a fraction in the exponent there. Okay? All right. And when you see a to the 1/2, right, when you see a to the 1/2, that really means the square root of a. So, for example, you know, when we had when we saw the square root of -2, for example, right? When we saw a square root of -2, right, that would set off little alarm bells in our head because the square root of -2 is going to be what kind of number? Imaginary, right? Okay. Well, now if you see -2 to the 1/2 power, that should also set off the same alarm bells. You're going to have an imaginary number. Okay. So just keep that in mind. All right. So let me summarize in general here. Okay. So the exponent m over n means the mth power of the nth root of a quantity. All right, and I'll show you what I mean by that with an example, okay? So if you see an exponent that's in a fraction m over n, okay, what does that mean? That means you're raising that number, whatever that, the base, you're raising the base to that mth power, but then with the nth root. Okay, mth power, but nth root. So let me show you what I mean by that. Okay, so for example, okay, if I see, or if you see 27 to the 2/3 power. Okay, 27 to the 2/3 power. What root does this problem have? What root does this expression have? What's the root of this problem? Square root, cube root, 4th root, 5th root? Which one is this one going to be? Cube root. Where do you look to see what the root's going to be? The denominator of the power there. Okay? The denominator of the power is what you want to look for. Okay? So this will be then the cube root of 27. But then what do we do with that 2? Well, the 27 is squared, like that. Okay? And we can simplify this. What's 27 squared? Well, I'll type it in here. Quick draw McGraw. 729. Okay? And then the cube root of 729, Well, let's see what it does. Hopefully it simplifies nicely. It does. It's 9. Okay. But we can also do it in kind of like a reverse order here. So alternatively, I could have also said here, instead of the mth power of the nth root, I could do the nth root of the mth power. So in other words, I could do it this way. Okay, these both mean the same thing. Okay, so these two things are equivalent here. These are equivalent. Okay, they will result in the same thing. So whether you put the exponent with the 27 inside the root, or whether you put the root inside of the exponent there, you're going to end up with the same answer. Okay, so the cube root of 27 squared is the same thing as the cube root of 27, that quantity squared. Okay, it's going to end up being the same thing, kind of interchangeable. Okay, now let's just simplify it this way. What's the cube root of 27? 3. What's 3 squared? 9. Okay, now, if you had your choice of trying to simplify these two things, all right, my recommendation here is to go with the cube, with the root on the inside, and then finish off by squaring, or whatever your exponent, or whatever your numerator is there. Okay, so do the root first, right? So in this case, it was over 3, so it was a cube root of the number, and then finish off by squaring. Why? Because when we squared first, we got this really big number, okay, 729, and maybe we're not as familiar with that 729, okay? So knowing that the cube root of that is, 9. Of course, you have your calculators, so you'll be able to use that. But if you want to try and do it mentally, and you can, a lot of these you should be able to do with your mental math, do the root first, and then square it, finish off with the numerator square in this case, so it gives us 9. But either way, you get the same answer, you see. Okay? All right, so what we're going to do now is we're going to practice going back and forth, okay, from going with rational exponents, right? Rational exponents are these, right? These fraction exponents, to these where we have radicals, okay? And then we're going to go from radical expressions to rational, okay? So they both start with R, but keep them straight, right? Radical means you have these root symbols in them, okay? And then rational means you have fractions that are fractions in your power there, okay? So let me just do some examples here. So again, we're going to translate from rational to radical expressions, or vice versa. Oh, is this going to fit? Womp womp. Okay, now it fits. All right, so let's just pick an example here. Okay, so first of all, is this in, right now, is it in rational form or radical form? Rational, our exponent is a fraction. Okay, you see no root symbols, right? You see no root symbols. So we're in rational form right now. We're going to change it to radical form. Okay, so what radical does this exponent indicate? What kind of root? Cube root. So the cube root of negative 125 to what exponent? The fourth, the numerator there. Okay, so this is one way to write it, or you could have written it as the cube root of negative 125, that whole quantity to the fourth, like that. So either of these are okay. So either the root goes inside the exponent or the exponent goes inside the root. Either way is fine. They're both equivalent. Okay? And in fact, let's go ahead and simplify this, right? What is the, and I'm going to simplify this one. What's the cube root of negative 125? Negative 5, very good. To the fourth, okay? And then so negative 5 times negative 5 is 25, times another negative 5 is negative 125, times another negative 5, I think that's 625. Let me check here. It is. Okay, that was more memory than actually calculating out in my head. Okay. All right, so there's our final answer, 625. That's pretty nice. Okay. By the way, you can, in your calculator, type in a rational exponent, right? There's nothing stopping you. So just please use parentheses, negative 125. Let me just show you here, negative 125 to the, and again, I would suggest you use parentheses in your exponent too, okay? Please make sure you use exponents, parentheses in your exponent. You hit enter, and there you get your 625 as well. Okay, so I'll do that for you too. All right, let's try another one. Okay, x to the 11 eighths. Okay, x to the 11 eighths. All right, so again, is this in rational form or radical form? Is this in rational form or radical form here, number 2? Rational, right? We got a rational exponent, right? No square root, no root symbols anywhere to be seen. Okay? But speaking of roots, what is our root going to be here? 8. So that's going to be the 8th root of x to the 11th. Okay? Or I could do the 8th root of x raised to the 11th power. Either one of these are equivalent. Okay, they're the same. I can't really simplify. Oh, no, I can simplify from here, can I? They're not going to have me do that. Okay, thank goodness. Good. This one technically simplifies some, but we're not going to worry about simplifying it right now. Okay, that's good. All right. All right, enough with that. Let's try one. Let's try 2 more here, and I'll have you guys try some on your own. All right, let's do the 5th root of 6 to the 4th. Like that. Okay? Is this in radical form or rational form? Radical. All right, so we're going to convert it to rational form. So our root here is 5, right? It's the 5th root. So what is the denominator of our exponent going to be? 5. Okay, and what's the numerator of our exponent going to be? 4, the exponent there, 4. Okay, and so there it is. Our answer is 6 to the 4 fifths. Okay, 6 to the 4 fifths. All right, let's try another one here. One more here together, and I'll have you guys try 1 or 2 or 3 or 4. We'll see. All right. 4th root of x to the 3rd. 4th root of x to the 3rd. Okay? So this becomes x to the, it's going to be a fraction, right? What's the denominator for our fraction going to be here for number 4? 4. And what's the numerator? 3. Okay, and there it is. Questions on any of that? All good? All right, let's have you guys try some here on your own then. All right. Let's see, I'll just scoot this up. We'll do it this way. All right, leave those up and I'll give you some to try. All right, so y'all try. I'm going to give you 4 to do on your own here. Let's see. Trying to write these very neat so that way, because these can be hard to. Okay, let's try and leave those up. Same directions then, same directions, okay? If it's rational form, change it to radical form. And if it's radical form, change it to rational form, okay? So see what you can do there with 1, 2, 3, and 4. Okay, see what you can do with 1, 2, 3, and 4. Does anyone still need to see those first examples? I can scoot it up some more otherwise. Anyone want to see them? All right, so I'll just do this then. Okay, can I leave those? I'll just leave them there. All right, so there you go. Give those a try. Okay, see what you can come up with. And try simplifying if you feel bold. Yeah, go ahead. Okay, some of these do simplify. I'll give you a hint. A and C, or 1 and 3 simplify. Okay, so I'll put little stars near those. I want you to try and simplify those too. Okay, 1 and 3 simplify. So see if you can get those simplified too. Of course, you shouldn't use your calculator, I guess, but don't use your calculator. Do it by yourself first. Stuck, need some help? Come around and help you. Like what to do? So you can try and simplify it. Fraction won't simplify it. The key thing here, so if you want to just answer the question, CJ, all you have to do is just convert this exponent to a root and exponent kind of thing. You see what I'm saying? So like you don't even need to worry about what's inside here. Just change it to what root does this exponent show, and then what power as well, kind of thing. And then just change it to that. So for example, you just got something that's being raised to the 3/4 power, right? So you just take whatever that something is, and you say, okay, it has the 4th root of that something to the third. That's all you gotta do. That's all you have to do. But then if you want to simplify it, you could try and simplify. You could actually cube it out and then do the 4th root of it and see what you get, kind of thing. Because 81, there's a 4th root to 81, and there's a 4th root to 16, so you can actually simplify those. Your choice. Well, that's all I'm asking you to do is just convert from one to the other. Okay. Other questions? Anyone else? Stop. Okay. I just want to check something too. Yep, I put parentheses around it, but that's exactly right. Yeah. And then, so that one, right, that fraction simplifies, doesn't it? Which is just 3, right? Well, actually, sorry, what's 6 divided by 3 is not 3. What does it simplify to be? What's 6 over 3? 2, which is just 2. So the exponent simplifies to 2. So it's 11 to the 2, which is the same thing as what's 11 squared. Do you know what that is? What don't you get? So all you're doing here, this problem, like number 1, all you're doing, you have something to the 3/4 power. So that means if you have a denominator 4, that becomes a fourth root. And then you cube it. So it's just you take that same something and you just do it fourth root of that something cubed. And that's all you got to do. If you want to simplify it further, you can try. You can actually simplify it further. I would actually recommend, though, for that first one, try and simplify it. So again, you can write it this way, or you can write it the fourth root of that something cubed. Okay. I recommend writing it this way if you're going to try and simplify it further, because it does simplify further. There is a fourth root of 81. There is a fourth root of 16. So, or a nice number kind of thing. CJ. 1 or 2 more minutes here, folks. Yeah, that's perfect. Yep, you can stop there if you want to. Yeah. Okay, you have these flipped, and you have the cube root of xy to the 5th. Because the denominator is your root, the numerator is your power. Okay, the denominator is your root, exponent, the numerator is your power. Okay. So you're good from there then? Okay. Questions, anything here? Nothing? You're good. Questions here? Oh, questions? Oh, okay. Well, yes.
Can I go, please?
So, yeah, the fraction of 6/3 simplified. If you want to go, go ahead. What's the fraction of 6/3 simplified to be? What's 6/3 simplified to be? Not 3/1. 2. No, you're not. It's actually funny. Tatum said the same thing too. There must be something about what we're talking about right now that makes it, kind of like that. But so yeah, it's 2. And what is 11 squared? So you can just say 121 every time. Say 121. Yep. So that fraction, you can try to simplify it, it won't simplify. There's no simplification. So you just rewrite it as 81/16ths, and then you're good. Right. And I'll show you, we can then simplify using the powers and stuff like that. Okay, we can simplify using the powers and stuff. Lots of people's on their phone, not trying these problems. I hope that means you guys get it. And you're just like, Mr. Witt, I don't even need to practice these. It's so easy, Mr. Witt. I hope that's what that means. I hope it doesn't mean that we're trying to avoid it because we don't understand it. Okay? Lots of people distracted right now. All right. So let's go ahead and go over these then. All right. So let's get out my volunteering app here. Start to sweat now. Whose number is going to come up? Julian, your number is up. All right, Julian. So this right here. All right. What root are we going to have with this problem? Fourth root. Yeah, fourth root. Okay, of 81/16 to the what exponent? Third. Okay. So, and that is a fine answer. Okay, that answer is fine. Let me zoom in just a little bit there. Now, you can stop there if you want to. I mean, we've done what the questions asked us to do. We translated from rational to radical. That's all you have to do. But I do want to show you an alternative way to write this, right? There are 2 ways to do this. Instead of putting the root on the outside and the cube on the inside, we could put the root on the inside. So we could say fourth root of 81/16 like this, and then raise the whole thing to the third. Okay? And either one of these simplify, right? It's just like I don't really want to cube 81 right now. That's a big number, right? I don't have to do that in my head. But I can do the fourth root of 81 easier. What number times itself 4 times will give you 81? What, and this is for anybody, right? What number times itself 4 times will give you 81? 18 times 18 times 18 gives you 18 times 18 times 18 times 18. That gives you 81? No, that's too much. 9 times 9 times 9 times 9 gives you 81? No, it's just 9 times 9. It's just 2 9s give you 81. What 4 of what number give you 81 when you multiply them together? 3, okay? 3. So the fourth root of 81 is 3. What's the fourth root of 16? Or what times what times what times what gives you 16? 2. So the fourth root of 81 over 16 is just 3 halves, and then we'll cube it. What's 3 cubed? 3 to the fourth is 81. What's 3 to the third? 27. What's 2 cubed? 8. And so there is your fully simplified. So again, these are okay. If you did this or if you said this, that's fine. But this one actually simplified nicely to 27/8. You could simplify it further. Okay, you could. All right. Next, let's go to Peyton. Peyton, for this problem right here, Peyton, what is my root going to be? Square root, cube root, fourth root, fifth root, what's it going to be? Okay, so xy is my base, but look at your exponent, though. What is the root going to be?
5.
Nope.
3.
So yeah, it's got to be the 3. It's the denominator. It's the denominator, okay? The third root of, you could do, again, of x to the 5th like that, or you could say, I'm going to run out of space here, the cube root of xy to the 5th on the inside like that. Again, either one of these is acceptable. This one or this one. Nope. They're equivalent. They're equivalent, okay? So cube rooting it first and then raising to the 5th is the exact same as raising to the 5th first and then cube rooting it. You're going to get the same result, okay? Same result there. Assuming that our variables are positive at least, yes. Okay? All right, let's keep rolling here. All right, CJ. CJ, number 3. Okay, now we're given a radical. We want to write it in rational form, CJ, right? So, well, the base is going to be 11. What is my numerator for my exponent going to be? 3, very good. And denominator, I should say, that's 3. What's my numerator? 6, yeah, okay, sorry about that. Now we get to an interesting point that we haven't seen yet. That fraction 6/3, what's special about that fraction? It what? It simplifies. What does it simplify to be, Mike? 6/3. What's 6 divided by 3? 2. Just 2. We don't have to do the 1/2. It's just 2 because it's the 6 is the bigger number on top. So it's 2/1 or just 2, which is 121. Okay? So the cube root of 11 to the 6th is 121. So yes. Long story short, yes, you can simplify. You can simplify fractions in your exponents too. Okay, those fractions simplify. Okay? All right, last one here. Let's go to Chris. All right, so Chris, here we have the cube root of the quantity 2x over y to the 5th. All right? And so that's going to be then 2x over y raised to a rational exponent here. What's the denominator of our rational exponent going to be here, Chris? Yeah, it's 5/3. Very good. You just give me the whole thing. Perfect. Okay, and there's our answer. Okay. There's our answer. Questions on any of that? All good? Okay, I want to show you just a little bit more here, and then I'll get you guys started on your assignment, okay? But we're not going to go very much further than that today. Okay, we're not going to go very much further than that today here. So let's see. All right. Actually, I'm going to go off this. I'm going to go to a piece of paper here that I have printed out. Oh, I already have the answer written though. All right, I'll just block it off. Yeah. Sorry, CJ. Is it okay if Nate goes for me? I know sometimes. Okay, very good. All right, thank you. Yes. Go ahead there, Nate, and then CJ. All right. I'm blocking off my answer that I have written here. All right. So, actually, I guess I should briefly talk about this up here. All right, so another thing we're going to look at here, just talking about modeling with power functions. Now, don't get, power functions are just functions that have exponents in them, right? So, like, you've been using these since, very early on, right, in your math career. Area, for example, of a circle, that's a power function because it's pi r squared, right? Volume of a sphere, power function because it's got a cube in there, okay? Here's one with a pendulum, okay? The time t in seconds for a pendulum of length L feet to complete one back and forth swing, okay? So these are all power functions. A power function just has the form y equals a times x to the b, where a is a real number and b is a rational number. This is like, you think exponential functions too, right? This is stuff you guys talked about back in Algebra 1, right? Well, never mind. Forget that. Sorry. Exponential functions are a times b to the x. Here the x is our base, so never mind. Anyway, okay? So let's take a look here. All right, so this is a biology question. You guys like some biology. All right, the function r equals 73.3 fourth root of m cubed is known as Kleiber's law, or Kleiber, okay? It relates the basal metabolic rate, capital R, in calories per day burned, and the body mass m of a mammal in kilograms. Hey, you guys are mammals. We're mammals. Oh yeah, I should have said we're all mammals. I'm a mammal too, right? I am not a living person. I am not. I would not have said you guys are mammals if I was an alien, right? That would not be. Anyway, no. So, just real quick. Basal metabolic rate. Okay? Basal means base. So it's like the baseline metabolic rate. That means how much energy you burn a day. Remember, a calorie is a unit of energy, right? Some of you guys are like, oh, I can't eat too many calories because it's going to make me fat. Well, yes. Energy, if you eat more calories than you're supposed to, right, then your body will store that energy as fat to use later, okay? Because, back in the day when we had to hunt for food and stuff like that, we might be able to find food plentiful, so we would store it in our bodies as fat, right? But now we don't want it, so we try and get rid of it, all right? So anyway, so if you want to know what your basal metabolic rate is, that means how many calories you need to burn at minimum per day, or how many calories you need to ingest at minimum per day. Right, that means without any sort of physical activity, etc. Just like your baseline, what you need to do to survive, kind of thing. You can plug your weight, your mass, into this formula. Now you'll need to know your mass in kilograms. So if you know your mass in pounds, you would take the number of pounds, divide by 2.2, and that's an approximation. But divide by 2.2, that'll give you your mass in kilograms, and you plug it in here, simplify, and that'll tell you how many calories you need to burn. Okay, baseline. Okay, and again, it's an estimate too, so don't freak out if you're like, oh, I'm supposed to have 1,000 calories and I eat way more than that. You guys are teenagers, you guys burn things, but this is an average baseline kind of thing, so don't freak out. Okay. My point is though, let's try and rewrite this using a rational exponent, right? So you can see here that m is the fourth root of m to the third, right? So what exponent would we rewrite this to be for m? Okay, we would have r equals 73.3 times m to the what exponent here? What's the denominator for this exponent going to be? 4. What's the numerator for the exponent going to be? 3. Okay, so it's just the same thing as 73.3 times m to the 3/4. Hey, look at that. And there's a lie. Roar. Okay, you can see there too, some different units here we could plug in. So you could plug in the 4.5, 55, 170, all that jazz. Okay. So, for example, let's see here. Cheetah. Okay, cheetah is 73.3 times 55 to the 3/4. Okay, whoops, off the screen. Right. So cheetah has to burn at minimum. At minimum, a cheetah needs to burns 1,480 calories. Okay, basal, very baseline. Okay, and I don't even know if that takes into account. Yeah, I don't know what that takes into account exactly. Is it just like your normal body functions? That's how much calories it takes? I'm not sure. Basal. What is a baseline? Okay. Okay, here we go. Another one here. Ooh. Does this one want us to... forget about that one. It's because it's got a negative exponent. Okay, and that's all the same. All right, never mind. That's what we'll do for that. Okay, so that was just little word problem stuff there thrown in just to see that. Okay, so let me get you guys started on your assignment then. We'll just go from there. All right, so this is going to be in 11-1. 11-1. And I'll get you a page number here in a second, but I'm going to have you do numbers 1 through 19. Odds. I'll get you a page number in 1 sec. Did I write it down here? I did. Page 386 in the book. Okay. 1 to 19 the odds. So you have 4 where you're going to convert rational exponents to radical expressions, and then you'll have 4 where you convert radical expressions to rational exponents, and then you'll have 2 word problems that you'll just need to read through. It's very simple to do the actual math, but you just need to read what it says, okay, and then do it. Okay? So, there's your assignment. Should be pretty straightforward. Pretty straightforward. So today we just focused on converting. Tomorrow we'll be, I think, simplifying these things, these expressions that we talked about. And then probably on Monday we'll start solving equations, okay?